Hey guys, welcome to my video on radical functions. This first video is going to talk about the first part of your packet, Unit 4, Part 1, where we're just going to talk about the graph characteristics and graph of a radical function. So, let's get started. These are the important topics that you're going to need to know. Alright, this is a brief overview. I'm not going to talk about anything really right now. So, this would be these right here, if I can get my pen, these right here are the important topics, all right? The first part is understanding what a parent function is. The second part is understanding where they get the parent table values from. And then this third part right here, transformations, that's really where we get into the nitty-gritty and we start talking about what's happening, what is truly happening to your graph based off of these parent functions and parent table values. And then last but surely not least, all of this. This is all stuff that you should remember or recall from Unit 3 with graph characteristics of polynomials. If you need a little bit more in-depth into that, you can go back and watch that video that I have on Unit 3. I think skip around to probably about the halfway point, 10 minutes into it, and I kind of go in depth about how we find domain and range, what are zeros, x-intercepts, and roots, what are the y-intercepts, and what is this end behavior, okay? So feel free to rewatch that. I will explain as best I can, but I'm not going to take up too much of your time. All right, moving forward. Here we have our parent function graphs. I went ahead and provided you with, this one is the first radical function we're going to look at. F of x equals the square root of x, okay? If you notice, the graph starts at 0, 0. There is not an additional arrow here. When we're talking about this square root function, you only have one arrow, and that arrow is right here, okay? Wherever you start your graph, you need to understand that this is a solid, filled-in, closed circle. That is an endpoint. There's nothing going on past that. Because by definition, a square root function, you are going to get values that are not real, okay? They're not going to work. It loses its ability to become a square root function. If you were in my class and you were in this lesson, remember I told you there exists this other parabola, okay? Right here, this line right here, there exists. What happens if I draw that in there? Well, if you're in my class, I told you, look at it. It doesn't pass the vertical line test. That is the reason why we're only looking at half of a parabola. We're only interested in the values that are real, okay? That make your function stay a function. That's what we're interested in, okay? That's what we are. And that's why, even if you're solving, I know I'm not talking about that in this video, but when you're solving, that is why we're always checking our answer with this square root, because again, there are solutions that will not pass the vertical line test, hence the reason why they will not be included in your function. There are values that will not make your function true. Okay? All right. So, that's the square root function. Over here, all right, we're transitioning to this right graph. This is a cubic function. Okay, not a cubic function, excuse me, that was very bad. A cubed root function. All right. This cubed root function, if you notice, it has an arrow here in quadrant 1 and an arrow here in quadrant 3. They're pointing in opposite directions. Okay? Opposite directions. Does it stop? No, it does not stop. A cubic function, we are looking at all x values, positive and negative, and we're looking at all y values, negative and positive, okay? It does not stop. It will eventually hit all of those values. That is very important for you to recognize that that function continues on and on forever in both directions. Very important. Very, very important. Okay. So this is what this looks like. These are the parent functions. There's absolutely no transformations going on with them. They are both cross through the origin. They both go through the origin. Right there, that's the origin, 0, 0. This one starts at the origin. This crosses through. And some of you in my class recognize that this is a snake through. It's snaking through the origin. Hence the reason why there's that 3. So that was a great observation on your behalf. Again, back to that unit 3. All right. That's what it is. That's what it looks like. Let's move on to the next slide. The next slide, we start talking about the table values. Okay? Logically, all you have to do is put it into your calculator. Ladies and gentlemen, your calculator, that TI-83 or 84, I don't remember what it is, that calculator, all you have to do is put this, technical error. You have to just put this right there, y equals, and that y equals button in your calculator. You know, it's up there on the tab, right next to the screen, and just put in the square root of x. When you do that, hit enter and press second graph, and that will give you these table values. We didn't just come up with these table values out of thin air. We found them mathematically, okay? We found them by plotting that into the calculator, and you can see as clear as day, those are the table values. Now, you might ask me, well, Miss Smith, I still don't understand that. Well, let's talk about this, okay? These table values, all right, we have this parent function. We just talked about that for a square root. That is the parent function. So the parent table, we are going to use very specific, all right, x values. I want to get nice numbers, all right? So if you recall, your x values in a function are independent values. Independent means that no matter what you do, those will always be there, okay? Your x values will always be there. You literally can put in any x value you want to, and you'll get some type of number, okay? It will happen. It just is there. It's literally like looking at your sister and saying, I have a sister. Yeah, you do. She's never going to go away. You will always have that sister, okay? It's the same thing. It is. It is, okay? So these x values are. That is what they are. It doesn't matter. It doesn't matter. What we have done for you as teachers is given you x values, these right here, we gave them to you to focus on these because in a parent function, that right there, you are going to get very, very nice dependent values right there in your y column. Okay? We have given you a guideline so that you are getting nice whole numbers and not decimals. Y'all kind of freak out when you have to deal with decimals and graphs because you're like, oh, I don't know where 0.3 is on a graph. Yes, you do. You just, you kind of get scared, intimidating, but you could graph it. But for the sake of ease, all right, for basically making it easy, we have provided you with this guideline, these x values, so that you get nice y values, nice whole numbers. All right, how do we get those? Well, if this is x right here, right, we take this x right here and we plug it into that square root. What's the square root of 0? Oh, that's 0. What's the square root of 1? Oh, that's 1. What's the square root of 4? Oh, that's 2, Miss Smith. Yeah, we're doing great. What's the square root of 9? 3. Perfect. What's the square root of 16? 4. So we have these very, very nice numbers, all right? Now, if we go back to this graph right here, if we go back to this graph, all right, let's take a look. Is this 0, 0? All right, remember, our parent function, our parent table said we had 0, 0, 1, 1, 4, 2, 9, 3. All right, I'm running out of room, so I'm going to stop writing. But let's check. Is this 0, 0? Yes. Is this 1, 1? Absolutely. Is this 4, 2? Yes. Is this 9, 3? And then finally, is this 16, 4? Yes. All of those relate to this parent table. It doesn't just come out of thin air. We don't just literally pull it out of a hat. It is there because our mathematics, the logic behind it is sound. Okay? I hope that helped connect something for you guys. Now, that is also why, because I'm going to start looking now at my cubed root function. That is also why we came up with -8, -1, 0, 1, and 8. Okay? These are all perfect cubes. So when we take the cubed root of all of these numbers, these x values right here, we take the cubed root of all of those values, we get whole numbers. Again, we are just directing your thought process so you're not sitting there scratching your head and going, well, they never taught me this. Yes, we did. We just simply want to guide your thinking. We want to give you a clear path. We want you to literally see the light. And that's where this comes from. Again, your calculator, this, to find the cubed root button, you press math, and then you go down to the number 4, and that will literally give you this button that goes 3, and then there's a parentheses. Okay? That is where your cubed root button is. All right. Now, I have these little asterisks with always because that's always going to be the table values you're going to use. That's what you're going to look for when they ask you for that first table, that x1, y1, that's what they want you to use, all right? The next thing that we're going to look at, if I can, get it to work. There you go. The next thing I'm going to look at is what I told you in class. Now, both of my classes, I made you create an organizer. Okay, I made you create something that will help you figure out what's happening, where is it going, what do I need to look at, all right? This is a general radical function, okay? We have y equals plus or minus a square root, all right? This is also interchangeable with a 3, a cubed root, x minus h plus k. Now, if you're in my class, I told you that I like to drop the radical symbol down, so make sure that you know there is nothing past it, okay? Or there's nothing else included in this. It is very important that you do not somehow, by mistake, include that k. It's not a part of what's underneath the radical, okay? It's not. So it's very important that you see that, and that is why I will drop it down. Sometimes I don't, but the majority of the time I will drop my radical symbol down. A lot of you ask me, is it a 1? It's not a 1, I'm just dropping it down. Okay? So, let me explain this slide. These are all of our transformations. This is what was the hardest thing to understand, is when we're talking about transformations, we're talking about this sign like it's something separate from A, okay? Because that sign, the plus sign, you're fine. The minus sign, though, this minus sign tells you that you're reflecting over your x-axis. So it's very important that you understand that even if that sign is there, if that negative sign is there, you need to put it in there. Like, you need to tell me that is a reflection over the x-axis. You need to know that that is separate from A, okay? So when we go to look at A, we're looking at these types of values. We're looking at any A value that is less than 1. This is less than 1 right here. And we're going to say it's a shrink. Now, we're going to talk about this being vertical, okay? It's a vertical shrink, and it's a vertical stretch, all right? It's a vertical stretch if you have A is greater than 1, 1, 2, 4, 5, whatever it may be. It's a stretch vertically, okay? You need to know that. And it affects your graph. Now, going forward, going to the next thing, we're looking underneath the radical now, underneath this house, all right? Underneath this radical symbol, we have x minus h. Now, whenever we're dealing with anything minus in a formula, It's telling you to do the opposite of whatever thing you're looking at. That is by default. Another important, like that, I'm trying to explain this to you in a way that it would connect it to you. This minus sign, if you ever did point slope formula, y minus y1 equals m times x minus x1, some of you might be like going, I don't know what you're saying. So just kind of skip ahead about a minute. That point slope form tells you to do the opposite of whatever ordered pair you're looking at. Whatever ordered pair you're going to put into the formula, you're doing the opposite of whatever it is, okay? So whenever we have a minus sign in any type of formula, the vertex formula, whatever, what have you, it's telling you to do the opposite. That is an important kind of thing, a connection to make, because it's not going to go away. Anytime you have a formula, I don't care what it is, even in science, when you have a minus sign, it is telling you to do the opposite of whatever value you have, okay? Hence the reason why I put a big old opposite there. All right. Now, that means when you have plus x, let's say we have x plus 6, okay? If we have x plus 6 underneath that radical, your first instinct, and something that you told me in class, was to say, oh, well, I know it's plus 6, so go to the right. And I'm going to look at you and say, no, now what did I just say about that minus sign? It means opposite. So you're really going to move to the left, all right? That is explained right here. Now, what I left off on the slide is that this is really a horizontal shift, okay? It's a horizontal shift right and left. You need to remember to say that because that makes you understand that it's on the horizontal axis. Which one is the horizontal axis? The x-axis. It makes sense. It's logical. Follow that path, okay? And then finally, last but certainly not least, we have this k. All right? This one's more straightforward. Y'all are much more comfortable with this. This is a vertical shift up or down. If it's positive, you go up. If it's down, if it's negative, you go down. There's nothing other than, like, it's just a very straightforward procedure, okay? It's very straightforward. Up, it's positive. Negative, it's down, okay? It's a vertical shift up or down. Don't overthink it. Embrace it. Embrace how easy it is. Just do it, all right? Hope that helps. Let's see. Do we have anything else to cover? Yeah, here we go. Getting into the graph characteristics. Now, I pulled this graph from Docere, so I need to make sure I add in my endpoints because you need to be able to see this. I'm going to put a big old arrow right there so I know that it's pointing down and it's continuing on forever and ever. I'm also going to add in a nice closed circle right there at 1, 2, that order pair 1, 2, because that's where my graph begins. That's where I'm beginning. So, looking at this graph, can I tell the domain? Absolutely. Remember what I told you. The domain is all of your x values. So, if you have to, draw your starting point down to that number. Now, I used the wrong marker for that, so I'm going to erase that, and I'm going to see if I can do a different color so that you can see this, okay? I'm going to drop this function down. What x value does it start at? Well, if you look, that x value is 1. So I can say my domain starts at 1. The question became, well, do I use a parentheses or a bracket? Since this is a filled in circle, okay, it will always be filled in, class. It will always be filled in. I know that I need to use a bracket. Okay, we use brackets when we have a filled in circle. Okay, when it's equal to, remember, inequalities, it's equal to. Okay, so I'm going to add a bracket around that 1. And I'm going to continue to follow my graph, okay, my line right here, this curve, until I get to the ending point. Now, the ending point, in this case, becomes this arrow. Where is that arrow pointing? Well, it's pointing to positive infinity. Now, can you ever equal infinity? The answer is no. Okay, hopefully you said no. So we know to use parentheses when it's not equal to, okay? Or it has an open circle, a gap in your graph, so to speak, or you're dealing with infinity, whether it's positive or negative, okay? Always use parentheses, okay? That is domain. Now, I'm going to erase this so I can you can see this. Put my little circle back in there. The range, okay? Notice the range, like this graph is sloping downwards, okay? So hopefully by now you've kind of figured out that this is probably a reflection over the x-axis, okay? It's a decreasing curve. You're sliding downhill, you're walking down those stairs, whatever you need to say to yourself to figure out that this is technically a negative graph. So when you have a negative graph like this, when it's reflected over this x-axis, we are now going to start looking at this and reading it from the bottom to the top. You're always going to be doing that. I'm just simply making you recognize what you're doing. So, as I told you, the range is all of your y values, so right there on this y-axis, and you're going to read from the bottom. If I can write, it's not letting me write. From the bottom, and you're going to go to the top, okay? So I'm going to take my highlighter, and I'm going to look. What is the first thing that I hit? Oh, look at that. It's this arrow again, this pesky little arrow. Now, it is pointing down, class. It is pointing down. Whether you think it is or not, I'm here to tell you that as this graph gets larger and larger and larger and larger, this function right here, this curve, is going to forever go down. Slowly, but it will eventually hit every single negative y value. So we're going to say that our range, okay, is going to start at negative infinity. Now I'm running out of room, so I'm going to put the range up here. I apologize. We're going to say it starts at negative infinity. And remember, I said if it's positive or negative, we use parentheses. After this, okay, after we do this, you need to now follow it up. Follow it up until it stops. And it stops right there. Okay? It stops right here. At what y value is that? Yes, it's at 2. And since it's a filled-in circle like I had before, it's a hard stop, it equals 2, I can say my range is from negative infinity to 2. All right, next thing. I know this video is getting a little bit long. Roots. The roots of this function is where it crosses your x-axis. Where does it cross my x-axis? Oh, it crosses at 2. So I would say x is equal to 2. My y-intercepts. Does it cross my y-axis? No, so I would write none. Now, end behavior. Can I teach you a little trick about end behavior? End behavior is basically telling you and asking you, well, what do you know about these endpoints? Well, we have an endpoint right here, right there, and then we have an endpoint right here. So basically they want to know what exactly is happening there. So, as x is approaching or is at 1, y is at what? What is happening? As x approaches 1, okay? As x goes to 1, where does y go? So this is where some backward thinking comes into place, okay? So as x goes to 1, y, all right? Because look, as x goes to 1, remember, we read the graph from left to right. We're technically reading it how it goes down, okay? Again, we're reading it from left to right, so that's the key to remember. As x goes to 1, y is actually going to negative infinity, okay? again, we read our x-axis from left to right, so you need to make sure you understand that, or else this is literally like the most backward things you ever heard. But as x goes to 1, y is sloping downwards and it's going to negative infinity. Okay? Now, as x goes to infinity, okay, so as our x values, we continue, watch what happens. As x goes this way, and we're starting to check out our y is actually going to end at 2. At 2. It's going to end right here at 2. All right? So that's what we say. Now, the trick I was talking about is this. If you notice, this line right here is the same thing as our x's in our domain and range. Okay? And then, as we continue to look at this, I don't know why it's not letting me do it. There we go. This, as x goes to positive infinity, y goes to 2. That's this line right here. We can make a general statement that that's going to be the case. Those are the things that you can think about, and you can think smarter, not harder about. Okay? I'm going to erase everything. Hopefully you got it. The next thing we're going to look at, and the last thing we're going to look at, is the same thing, but the characteristics of this right here. This cubed root function, remember we have to add our arrows, all right, because it's going in both directions. Now, the nice thing about these graph characteristics of a cubic function, they're going to stay the same, always, okay? And I love always statements. They're always going to stay the same. So the domain and range will always be negative infinity to positive infinity. Domain as well as range. Because you have arrows in both opposing quadrants, this quadrant and this quadrant, okay? Even if this was shifted up some more and they were just going in opposite directions, it doesn't matter. By default of them going opposite directions, they're going to hit all of these x values and all of these y values by default. Okay, ladies and gentlemen. So don't overthink that, please. That is an easy understanding. You can easily get your points for that. So that's my thing right there. Now, roots. On this graph, there is 1 point right here. X is equal to -2. That is where it crosses my x-axis. Now, y-intercept. We do this time have a y-intercept, and because of the vocabulary that they use, we're going to actually write this as an ordered pair. Whenever they ask you for y-intercepts or x-intercepts, you have to write it as an ordered pair. Now, again, what did I just tell you about end behavior? This matches with this one, okay? And then this one matches with this one. So, let's write it out. As x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity. So there you have it, ladies and gentlemen. Those are the graph characteristics for radical functions. A square root function and a cubed root functions. If you have any questions, I tutor Wednesdays and Thursdays, and I can clear them up. Hope this helps somebody.